Okay, so we continue on with with a discussion of the last two tests that we can employ in order to determine the convergence or divergence of a of an infinite series. Okay. And later on this on this lesson, we will also address the issue that um, how would you be able to how would you be able to determine which test applies to a certain to a certain series or to a certain given a series, how would you know what what type of test can you use for that particular series? Okay. And while we will not be able to really generalize this uh the solution to this kinds of problem or to this kind of problems. Okay. What we will be able to do is to make recommendations on the sequence on how you can choose your test. Okay. We can actually make a sequence of which tests can be high in your priority. Okay, and which test can be low in your priority. Okay. So which test would more or less give a certain result that you really needed in one or two attempts. Okay, and place those tests that are really that pose some challenges. Okay, in your into your solutions. Uh, and would yield results that may fail. Okay, that has chance to fail. So we'll put that last. But while we cannot recommend but while that is while those recommendations may be general, okay, the best way to to actually get a grasp of those guidelines and to really determine which tests applies to a certain situation is through practice. Okay, so you may be you may look for you may look for a text on this, okay, on infinite series on most calculus books. Most calculus books would contain one of these chapters, one of these topics as chapters. Then try to look for texts that would contain really numerous exercises. Okay. Um, in particular, I am using the book by Larson and Edwards. It's the title is Calculus. Okay, so I'm using the book authored by Larson and Edwards. So that's one book that I am using, and that book actually contains numerous exercises about this. So you may want to consult the book and try to look for exercises and then try to practice. Okay. So as I mentioned, we will discuss the last two. Okay, the last two tests. Okay, which is the root test and the ratio test and the root test. Okay. So the ratio test, okay, is stipulated in Theorem 17. Okay, so let the sum of an be a series with non-zero terms. And this is not necessarily this series is not necessarily a positive series. Okay, at this point, whatever will be considered na or whatever the series we will consider is either a positive series or an alternating series, okay, or a series would contain positive and negative terms. Okay. So if we want to be particular with a positive series, okay, it's either that we will be able to see it we will be able to see it from the end term itself, or if it doesn't show, like for example in this case it simply says summation of an, we'll have it as we'll have it as a series that is general. Okay, this is a general series, which means this may contain positive and negative terms. Not necessarily alternating, but may contain positive and negative terms. Okay, unless the theorem states so. Okay, there are theorems that explicitly state that the series should be a positive series. Okay, so if it doesn't state that the series needs to be a positive series, okay, then this one would pertain to any kind of any general series. Okay, and this one is its positive series. Okay. So again, what is stipulated in theorem 17 is that an, or the sum of an, converges absolutely if the limit of this ratio, okay, as n approaches infinity is less than 1. Okay. If the ratio of the succeeding terms and the preceding terms of a series is less than 1, then we say that the summation that the series converges. While if it is greater than 1 or infinite, okay, the series diverges. The problem is encountered when that ratio is actually equal to 1. Okay, because we will have no choice but to say that the ratio is, or that the test is inconclusive when that ratio is equal to 1. Okay. So to what type of series can we apply ratio test the most effective? Okay. Series that involves factorials or exponentials, okay, which can converge if they converge rapidly, okay. If they converge, they would converge rapidly, or if they would diverge rapidly also, okay. So series that converges or diverges rapidly, okay, can actually be tested using ratio test. And number one, it would be easier to do the operation, okay. And number two, most of the time they would return either it would return to it would return a ano a conclusive result, okay. So it's either it would tell that it would converge absolutely, it would diverge. Okay. And there are times that the ratio will become inconclusive. And when the time comes, then we will have to do some other test. Okay. Later on, you'll be when we rank these tests in terms of the priority of use, you would be seeing that this test is actually third of the four, uh, is actually in tier 3 of the 4 tiers that we will use, okay, to rank this tests. It means that this is close to last resort. Okay, so it means that if because the upper rank of our tests, okay, would be dedicated to those that have special forms, that have special that have that for example, for geometric series, for alternating series, okay. Those would occupy the top tier of our tests, okay. And the lower tier are those for general um, tests, okay, or for general forms, okay, tests that can be performed on general forms of series, okay. So if you are on the third or the fourth, it means that you're on the more or less on the last resort of tests that are available to you, especially when you're on the fourth, okay. So it means it's the only test available for you to do, okay, because of the form of the test, okay. So here, okay, we again take note that we can apply the ratio test if our series would contain exponentials and factorials. If your series would contain exponentials and factorials, one of the better tests to use is um the ratio test. Okay. So let's try that in example 30. Okay. So example 30, we're asked to determine the convergence or divergence of this series. Okay. So here it contains both an exponential and a factorial. So this is a good candidate for your ratio test. So for ratio test, we have to evaluate the limit of the absolute value of an plus 1, the succeeding term, and the previous term, okay, as n approaches infinity. Okay, so here we have an here to be 2 raised to n over n plus n factorial, okay, over n factorial, okay. So an plus 1 is 2 raised to n plus 1 over n plus 1 factorial, Okay. Now we substitute these 2 here. So we'll have the limit of an plus 1 is 2 raised to n plus 1 over n plus 1 factorial. Okay. Now, we will multiply that with the reciprocal of an because an here is in the denominator. So that means we will have to take the reciprocal of this an. So that we simply just multiply it here. Okay. So we will have n factorial here divided by 2 raised to n. So as n approaches infinity. Okay. So we take note, okay, first we take note that 2 raised to n plus 1 is 2 raised to n times 2. Okay. So that this 2 raised to n times 2 actually cancels, this 2 raised to n here would actually cancel this 2 raised to n here. Okay, so we can write it this way. This is the limit of 2 raised to n times 2. Okay. And we also take note that n plus 1 factorial is n plus 1 times n factorial. Okay. So n plus 1 factorial is n plus 1 times n factorial. Okay. This basically represents the rest of the factors for the n plus 1 factorial. Okay. So we can write it as n plus 1 multiplied to n factorial. Then let's multiply it with n factorial over 2 raised to n. So we evaluate the limit as n approaches infinity. So this one and this one, those factors cancel themselves out, while this factor, this n factorial and this n factorial cancel themselves out as 1. Okay. So this becomes now the limit of 2 over n plus 1. Okay. As n approaches infinity. Okay. Which is positive, obviously. Okay. So we need not to really have this absolute value here because 2 raised to n 2 over n plus 1 is basically a positive number. So we'll just have it as the limit of, and then I'll just divide with 2 raised to n. I mean I'll divide the numerator and the denominator by n. So I'll proceed by having this as 2 over n divided by 1 plus 1 over n. So that when I evaluate the limit of this is 0, this is 0. So this becomes 0. So the limit of this is 0. And according to Theorem 17, okay, according to Theorem 17, okay, the limit is less than 1. Okay, so the limit is less than 1. And as per the first assertion of the first of Theorem 17, okay, your given series converges. Okay, and again, we have been arguing earlier on, we have been arguing this to be convergent because of the fact that that factorials converge faster than, or grow faster than exponentials. Okay, so that's our argument before. Okay, if you can go back to lesson I think 4.2 and 4.3 somewhere there. Okay, we were able to find that this series such as this actually converge. And our assertion, our proof that this series actually converges is because of the fact that factorials, okay, factorials grow faster than exponentials. Okay, and since the denominator grows faster than the numerator, okay, then evaluating the limit of this using the or evaluating the limit of this would lead you to actually have this approach 0. Okay, so that's how we compute the limit of this, and that's how we actually were able to assert that this is a convergent series. Okay, so that's how we do it earlier. Okay, so there. Okay, so proceeding now with example 31. So again, for letter A, we have here your an to be n squared multiplied to 2 raised to n plus 1 over 3 raised to n. Okay, so your an plus 1 is n plus 1 squared multiplied to 2 raised to n plus 2 divided by 3 raised to n plus 1. So that this limit, when you evaluate this limit as per Theorem 17, okay, you have this as your an plus 1, and this is the reciprocal of your an. Okay, so we take note that we can cancel this, and what remains is 3. Okay? We can cancel this, and what remains is 2. Okay? So we have here 2 times n plus 1 square over 3n square. Now, multiplying this out, okay, so we have here n square plus 2n plus 1 multiplied to 2. So we have 2n square plus 4n plus 2. While the denominator is still 3 n square. And then to evaluate the limit of this as n approaches infinity, we divide everything by n square. So what is left is 2 plus 4 over n plus 2 over n square divided by 3. So we know that as n approaches infinity, this is 0, this is 0. So what is left is 2/3. And since this limit, okay, is less than 1, okay, is less than 1, as per the first assertion, the first point of Theorem 17, this given series converges. Okay. For letter B, this is n raised to n over n factorial. Okay, so that's your a sub n. Okay, so your a n plus 1 is n plus 1 raised to n plus 1, okay, divided by n plus 1 factorial. So that by Theorem 17, if we set up this limit, okay, if we set up this expression to evaluate this limit, we will have this. So n plus 1 raised to n plus 1 over n factorial multiplied to the reciprocal of an, okay, which is n factorial over n raised to n. Okay. Now, we see that this can cancel out, okay, and what is left is n plus 1, okay. And of course, we cannot cancel this out because these are powers. So what we can do is we can simply have this as the limit of n plus 1 raised to n plus 1 over n plus 1 times n raised to n. But recall that since this has the same base, okay, I can actually cancel one of this, okay, and then another one factor of this. So what is left is this n raised to n plus 1. N plus 1 raised to n. Okay, which can be written this way. Okay, because they have the same exponents, I can actually write them as a single ratio. Okay, and rewriting this in a very familiar form, okay, that allows me to evaluate this limit. Then this the limit now becomes e, okay, which is basically greater than 1. Okay, that limit is greater than 1. So as per second assertion of Theorem 17, if this limit is greater than 1 or is infinity, then the series diverges. So we conclude that A converges while B diverges. Okay, so that's for example 31. Example 32. Okay. Here this is an alternating series. Okay. But since this is an alternating series, okay, if we let an to be this one, okay, just take note that the limit as imposed as required, the limit to be evaluated as required by Theorem 17 is the ratio of the absolute values of the terms of an and its succeeding terms. Okay, baliktad, the succeeding terms of an, okay, and its previous terms. But the point is that you need to take the absolute value. So in that case, this can be ignored inside this absolute value. Okay, because basically this just tells you some of the terms are positive, some of the terms are negative. Okay, so we can simply make this as we can ignore this if we are inside the absolute value sign. Okay, and simply write that your an plus 1 is basically the negative 1 raised to n plus 1 multiplied to square root of n plus 1 over n plus 1. 2, I mean. So this is n plus 2. Okay. But again, if you put it inside the absolute value, this gets to be ignored. Okay. So we have here square root of n plus 1 over n plus 2. Okay. Multiplied to the reciprocal of an. Again, with the negative 1 raised to n ignored because you are inside the absolute value. So you have this one. Now, I'll combine, I'll rearrange this so that I can write it this way. okay, in which I can using the properties of limit, since this is multiplied. So the product of the limits of this product is the product of their limits. So I'll have this and this. Okay. So I can separate them into two limits and multiply them eventually. And okay. And basically I divided the terms inside they are divided by n. So you'll have 1 plus 1 over n over 1. Okay. So that if you actually uh, get the um, limit of this becomes 0 still. So this becomes square root of 1. Okay. So that's the square root of 1. While here, okay, this becomes 0 and this becomes 0. Okay. So therefore, the limit of this is 1 over 1 or 1. So basically, the limit is 1. And what does the Theorem 17 tell us if the result is 1? If the result is 1, your series is, we don't have any conclusion yet. Okay, we don't have any conclusion with this one. Okay, it's because the third assertion, okay, of Theorem 17 says that if this limit is actually equal to 1, the ratio test is an inconclusive test. Okay, so which means that the ratio test is not really a good test of convergence or divergence in this case. Okay, so in that case, okay, we need to employ a better test. Okay. So since we have already seen that the series is actually an alternating test. I mean an alternating series. Okay, we can use theorem 14. Okay. And again, if you recall theorem 14, you need two requirements. Number one, okay, number one, that um the succeeding terms are less than the present terms. Okay. And number two, that the limit of the n term, okay, is the limit of the n term lang ha, not n plus 1 term. So the limit of n term, okay, is 0. The limit of n term as n approaches infinity is 0. So that's theorem 14. Okay. So how do we find if the terms are decreasing, or how do we find if the succeeding terms are less than the previous terms? Okay. Again, I have you can actually prove this analytically, okay, or by finding the first derivative. Okay. If you use the first derivative test, you need to remember that first you need to consider that the series is actually that the series is actually a positive series. So we will have to resort to the positive the positive part of the series. Okay. So in that case, we will have to ignore the negative the this factor that tells us the sign of the terms. Okay. And simply deal with square root of you start with the square root of n plus 1 over 1 n plus 1, and then you convert it to f of x so that you can get the derivative. Okay. Again, this is a discrete function. Okay. We need a continuous function to be able to get derivatives. So we converted it into f of x. Okay. And its first derivative is this one, which if you would inspect for positive x, okay, this factor is positive. Okay. Of course, this factor is positive. Okay. And so therefore the denominator is always positive. Okay. So the sign is determined by the numerator. And since the numerator is simply negative x plus 1, as long as your x is actually greater than 1, for example, 2, okay, if x is 2, okay, then f prime of x, the derivative, is automatically negative. And that happens for all x greater than 1, for all values of x greater than 1. So therefore, we are assured that the terms are decreasing and that we comply with the first requirement of Theorem 14. Now, for the second requirement of Theorem 14, we evaluate the limit of the positive series for the positive terms of the series. So we have here the square root of n over n plus 1. Okay. And using Hopital's rule in this case, okay, I've used Hopital's rule to evaluate this limit. So you have 1 over 2 square root of n. That's 1 over 2 square root of n over 1. Okay. Its limit as n approaches infinity, okay, is basically this is 0. Okay. And this is 1. Okay. So, um, in that case, that means that we were able to comply with the second requirement of Theorem 14. So Theorem 14, or the alternating series test, actually tells us that this series, okay, this series, the summation of square root of n over n plus 1 is a convergent multiplied to -1 raised to n, for n equals 1 up to infinity, okay, is actually a convergent series. Okay, unfortunately, ratio test would not be conclusive, okay, if used to test the convergence of this test. I mean of the series. Okay. So what was used to settle this question? What was used to settle the question of whether the series is convergent or not is the theorem 14, which is the alternating series test. Okay. Now, so we now proceed with the final test, okay, that we will study, which is the root test. Okay. So, the root test would work well with n terms having n powers. Okay, if your series, or if your n term contains powers of n, which means the exponents are n themselves. Okay, and the exponents are n themselves, then the root test is actually a good way to deal with those kinds of series. Okay. So there are three assertions for theorem 18. Number one, if the nth root of the n term, the positive n term, if the limit of the nth root of the n term, okay, of the series is less than 1, then we have a an absolutely convergent series. While if it is greater than 1 or infinity, we have a divergent series. The test is inconclusive if that limit is actually equal to 1. Okay? So, the root test, again, would work greatly, okay, for series whose n terms contains powers, okay, powers of n, okay, which means that they are, they have exponent of n, okay. So, like example 33, you see that n and n here are the exponents. Okay, so in this case, root test is very convenient to apply. Okay, so we find that a n here is e raised to 2n over n raised to n, or basically, let's have this to be e square over n raised to n. That's your an. Okay, so we evaluate the limit of the nth root of the positive series for this, or the positive n term for this, okay, as n approaches infinity. So we have the limit of the nth root of this one, which is e squared over n raised to n, okay, as n approaches infinity, which, as you can notice, this nth root and this raised to n would actually cancel themselves out. Okay, because basically, this can be written as the limit of e squared over n raised to n, then raised to 1 over n. That's the nth root. So the exponents would cancel themselves out because the ratio becomes 1. Okay. So what remains is the limit of e squared over n as n approaches infinity, which is basically, this is a constant divided by n. So basically, this is 0. Okay. Now, since the limit of nth root of the nth term, or the positive n term of your series as n approaches infinity is less than 1 because it's 0. Sorry. It's less than 1 because it's 0. Okay. The series, okay, the series is convergent. as per the first assertion. Okay, it's the first assertion of the root test. Okay, so that's how we determine the convergence of or how we use root test. Okay, so as promised, first we summarize all of the tests that were discussed from lesson 4.2 up to this is I think lesson 4.6. Okay, so yeah, I think this is lesson 4.6. So we will we summarize them. So we start with the end term test for divergence, which is theorem 9. Geometric series, okay, which is under theorem 6. Okay. The telescoping series, which is not really covered in which do not have any theorem, okay, which is not specified in any theorem, but is covered in lesson 4.2, if I'm not mistaken. Okay. So next we have the P series. Okay. So these are the requirements. Okay, or conditions. We have the alternating series under theorem 14, the integral test under theorem 10, the root test and the ratio test under theorem 18 and 17 respectively, and the direct comparison and the limit comparison under theorems 12 and 13. Okay. Actually, this arrangement is the arrangement of the priority. Okay. How the prior the which test would you prioritize to look for first? Okay. And that means that the direct comparison and the limit comparison are the court of last resort. These are tests of last resort. It means that if everything else fails, okay, if everything else fails, from theorem 9 to theorem 6 to the P series to the alternating series to the root and ratio test, especially these two, okay, if these two still fails, okay, you don't have the last test that you would be able to employ is theorem 12 and theorem 13. Okay, so this is the list of priority. Okay, so skills in choosing and applying the various tests will come only with practice. Now, this is the set of guidelines. Okay, this is just a suggestion. Okay, but the use of the use of this test in their in this particular order, and the skill in order to determine which test actually applies to a certain series uh, by just merely looking at the form of the series actually comes from the practice and experience. Okay, so again, it is suggested that you find books or you find texts which discuss, okay, or which presents this lesson, okay, so that you'd be able to look for exercises and try to use the guidelines, use these guidelines, and later on be able to um have a mastery, okay, of determining which test can actually apply to to a certain um to a certain series. Okay. So let's try them in example 34. Okay. So letter A. Okay. So letter A. I'll work on the first few examples here. Probably A and uh I'll try F and G. Okay. I'll try these three examples. But anyway, all of all of them have been have been solved yet. Okay. So I'll just I'll just walk you through, okay, walk you through with with the thinking process, okay, on how to use these guidelines, okay, and how they apply into this okay. So letter A, we have here the summation of n plus 1 over 3n plus 1 as for n equals 1 up to infinity. So we'll determine the convergence or divergence of this series. Okay. Um, this is a very simple series, no? This is a very simple, the end term of this is very simple. This is simply n plus 1 over 3n plus 1. Okay. Now, according to the guidelines, okay, according to the guidelines, what we will try first is the nth term test for divergence. We will try Theorem 9 first. Okay. So here, let's try Theorem 9 by evaluating the limit of an as n approaches infinity and see if this is uh, equal to 0 or not. Okay, because if this is equal to 0, our test is inconclusive. Okay, but if this is not equal to 0, then this series would diverge. Okay? So that's the requirement for your theorem 9. Okay? Again, theorem 9 requires you to evaluate this limit. Okay? And if this limit is 0, then this test is inconclusive. We'll try another test. But if this test returns a positive a number other than 0, okay, then we can conclude that this series is um, a divergent series. Okay. So here we have here. So we have here. Okay, we have here the limit of n plus 1 as over 3n plus 1 as n approaches infinity. We divide the numerator and the denominator by n. So we'll have the limit of 1 plus 1 over n over 3 plus 1 over n as n approaches infinity. So this is 0 and 0 as n approaches infinity. So therefore, the limit is 1/3. Okay? So since the limit is non-zero, by Theorem 9, Theorem 9 is n-term test for divergence. N-term test for divergence. This is a very good time to look back into your notes. And actually, what I did was I also did summarize them. Okay, under this whiteboard also, I have here a summary of tests. Okay, we have I summarize here a summary of a table of tests. Okay, so as we work along in these examples, I would like you to check, okay, to look back into these notes and verify the conditions, okay, or the requirements of each of the tests. Okay, so in this case, I'm using Theorem 9 for number 1. Okay, so I'm using Theorem 9 for number 1, so which requires me to evaluate this. Okay, this limit, and if this is non-zero, if this limit is non-zero, then your series is divergent. Okay, so going back to that example, which is yan. Okay, so by the n-term test for divergence, okay, or by Theorem 9, this series is divergent. Okay, so that's for letter A. Okay, let's try letter F. Okay, so F is again the solutions for other numbers are discussed here. I'll leave them to you as to figure out how the thinking process the thinking process of choosing what type of test can be used. Okay, and mind you, when I am when I was trying to solve these problems, okay, I did have a share of doing some trial and errors. Okay, although the book already solved this problem, the reference book that I was using had a solution for this. Okay, but the best way to actually learn this is to try them first by yourselves and then try to look at the solution. Okay, that's the best way to practice on this. Okay, to practice solving these kinds of problems, because you really have to engage yourself in the thinking process on how to choose the proper test. Okay, so for letter F, this is the summation of n factorial over 10 raised to n as n equals 1 up to infinity, for n equals 1 up to infinity. Okay, so this contains a factorial and an exponential. Okay, if this contains a factorial or an exponential, okay, ratio test apply no yeah, ratio test applies here. Okay, because this might converge or diverge very quickly. Okay, because the factorial and the exponential becomes large for a very short, not so large values of n. Okay, so this might converge or diverge very quickly. Okay, so that is why we'll use ratio test in this case. Okay, so to use the ratio test here, we have an, the n term, as n factorial over 10 raised to n, and an plus 1 equals n plus 1 factorial over 10 raised to n plus 1. Okay, so Theorem 17, okay, Theorem 17 requires us to evaluate the limit of an plus 1 over an as n approaches infinity, okay, which is the limit of n plus 1 factorial divided by, let's put in some ruled lines. Feeling ko gumaganda yung sulat ko kapag may ruled lines. Okay, so n plus 1 factorial over 10 raised to n plus 1 multiplied to the reciprocal of a sub n, which is 10 raised to n over n factorial. Okay, so we evaluate the limit of that as n approaches infinity. Okay, so as you were able to recall earlier, okay, you would be able to cancel this and leave a 10 here. Okay, while you can cancel this and this, you can divide them and leave n plus 1 there. Okay, so what remains would be, the limit of n plus 1 over 10. I don't have to put the absolute value because I am now sure that this is a positive series. Okay, as n approaches infinity, which clearly approaches infinity. Okay, because this is infinite over 10. This is not an indeterminate form, no? This is not an indeterminate form. This is clearly an infinite number. Okay, and according to Theorem 17, number 2, second assertion, okay, if this limit, since the limit an plus 1 over an as n approaches infinity is equal to infinity or approaches infinity, the series diverges. Okay, so that's how how we apply ratio test here for letter F. Okay, we can actually confirm that here. Okay, the series diverges. And obviously for letter G, you would apply the root test. Okay, so I think I'll leave letter G to you. Okay, I'll leave letter G to you because this is basically just simply a root test. What I would like to work on instead is letter C, because this is a more interesting problem than letter G, because letter G is obviously or for letter G you'll obviously use the root test. Okay, basically because this is a power of n. Okay, if this is a power, if this is n raised to n, something like n raised to n, the root test is very suitable here. Theorem 18 is very suitable for letter G. For letter B, this is a geometric series. Okay, and you might be thinking, said, can we also apply root test here? No. Before you apply root test, you apply the test for geometric series. Okay, this is a geometric series. You apply root test if the form is something like n raised to n. Okay, but it is something like a constant raised to n. Use or try to look if the series is a geometric series. Okay, because more or less this is a series that have this form. Okay, are geometric series. Okay, so I try to look for look at letter C na lang. Okay, so letter C is the sum of n times e raised to negative n squared for n equals 1 up to infinity. Okay. Here are the list of kasi this is a very peculiar form, no? Okay, pero here are the list. Okay. 1. Does the n term approach 0? Okay. We're not sure. Here, the n term would not approach 0. Okay, because you have n as a factor. Okay. But don't conclude that the series is already divergent because there is a multiplier that actually decreases. So we don't know. Actually, that factor actually decreases faster than the n that is multiplied to that. This e raised to negative n square actually decreases faster than this one is increasing. Okay. So in that case, we will not be able to conclude whether this series is convergent or divergent. But one thing is clear. Theorem 9 would not apply here. Okay. Now, can we consider this to be geometric? No. This is not a geometric series. Is this a P series? No. Okay. Is this a telescoping series? No. Is this an alternating series? No. Okay. So we'll go to the third tier, which is about the integral test, the root test, or the ratio test. Now, in between the integral, the root, and the ratio test, okay, the integral test would actually seem more logical. Okay, it would seem the more logical test that can be used in this in this given series. Okay, because you will not be able to use the root test. Okay, since this is just an exponential. Okay, and the ratio test, which might work, but might be difficult to deal with. So let's try the integral test. Okay, let's try the integral test here. Okay, so for us to be able to try the integral test, let's first have an equals ne raised to negative n squared to be expressed in terms of the function of x. Okay, as x e raised to negative x squared. Now, since we'll be using or we are attempting to use the integral test, one thing that before you spend your time, dealing with or determining whether it is positive, continuous, and decreasing. Okay, whether f of x is positive, continuous, and decreasing. These are the three requirements for an integral test. Remember. Okay. Before you determine that, you first try to ask yourself if you can integrate something like this. Okay. If you can integrate something like this, which is basically integrable naman. Okay. That's just simply e raised to u du. Okay, we'll show it later. But something like this is integrable. Okay. So since this is this we can we can integrate this one. We first determine is the series positive. Okay. So for positive x, since our x naman is positive, then remember that the restriction here is that your x is greater than or equal to 1. Okay. That is the limit of your summation, the lower limit of your summation. So we start your limit here. So for positive x, then you can say that this one is positive. Okay. Number 2, is the function continuous? Yes. Okay. Parang wala namang there is no weird thing about the continuous. Okay. There's no weird thing about the function that would not make it continuous. Okay. Now, number 3 is the function decreasing. Okay. Now, we can argue it this way. We know for a fact that exponential having negative exponents are decreasing functions. Okay. Much more that x is actually increasing when in this interval because you're increasing x. So therefore, your e raised to x becomes more and more negative. Okay, I mean the exponent here becomes more and more negative, and that makes it e raised to negative x squared more and more decrease as x is increasing. So this is so even if you multiply it with x, even if you multiply that with x, that function is still a decreasing function. Okay. So that's one way to argue that. Okay, that the function is actually a decreasing function. Another way is let's try to argue using the first derivative. Okay. Again, for us to say that the function is decreasing, we need to say that the first derivative of your function is negative. Okay. So here we take the first derivative of your of your function, which is we'll use product rule because this essentially is a product of two functions, x and e raised to negative x squared. So you'll have x here multiplied to e raised to negative x times the derivative of negative 2x. Okay. We use chain rule for this one. We use the first part of the product rule and then chain rule for the for determining the derivative of e raised to negative x squared. And then this is plus e raised to negative x squared multiply to the derivative of x, which is 1. Okay, so essentially, the first derivative becomes negative 2x squared e raised to negative x squared plus e raised to negative x squared, which we can see both terms contain the factor e raised to negative x squared. So we'll have this as negative 2x squared plus 1, okay, multiplied to e raised to negative x squared. This is your first derivative. And clearly, for positive, for x greater than or equal to 1, okay, okay, this factor is always negative for positive x. Okay, because even if x is set to 1, negative 2 is still greater than positive 1. So therefore, if you add these two, the least negative or the most negative, the greatest number that it can actually achieve is negative 1 when x is equal to 1. Pero from there, it becomes more and more negative. Okay, so therefore, we can say that your f of x, f prime of x, is actually negative. So that, again, proves our assertion from the start that our function f prime of x is decreasing. So since your function is positive, continuous, and decreasing, we can continue on with the integral test. Okay, so in the integral test, we take the integral of f of x dx from 1 to infinity. Okay, so we have here, or basically this is the limit of the integral ng b from 1 to b ng x e raised to negative x squared dx for b approaching infinity. Now, let's first concentrate on evaluating this integral. Okay, so I let u to be equal to negative x squared so that its differential, okay, is negative 2x dx. Okay, so as you can see, you can find x dx here. This is x dx. Okay, so what is missing is negative 2. So if I can actually insert negative 2 here, I need to balance it out by writing negative 1/2 here, so that I'll have the my original integral. Okay, so that I can proceed now as negative 1/2 times the limit of the integral of e raised to u du from 1 to b as your b approaches infinity. Okay, which gives us negative 1/2 times the limit of the integral of e raised to is e raised to u. Okay, and u is negative x squared. So this is simply e raised to negative x squared. This is from 1 to b. Okay, as your b approaches infinity. So we will have negative 1/2. We will evaluate this. We will substitute this 2 first. So we will have e raised to negative b squared. Okay, minus e raised to negative 1. Okay, as your b approaches infinity, or simply this is negative 1/2 times the limit of e raised to negative b squared as your b approaches infinity plus 1/2 e raised to negative 1. And essentially, if you evaluate this limit, since you will have a very large number for this b, okay, and it's a negative exponent of e, this essentially becomes 0. Okay, and so this integral, the integral of f of x dx from 1 to infinity is essentially 1/2 e raised to negative 1, or 1 over 2e, which is a finite number. And that indicates that this integral is convergent. Okay, is a convergent integral. So again, by theorem 10. Okay, as you can notice, I am looking at my my código here. Okay, I have here a small note listing all the theorems. Okay, so by theorem 10, okay, parang I have a cue card here so that I know which theorem to apply. Okay, so by theorem 10, okay, since your integral, okay, is convergent, okay, that will also mean that your series n e raised to negative n squared for n equals 1 up to infinity is also convergent. Okay, so that is for letter C. And letter C allowed us to use the integral test. Okay. So, actually, as you can, there. Okay. As you can see, the integral test is actually on the third tier. Okay. On the third tier of tests, alongside root and ratio test. Okay. Um, if I am to design this, I would have put the integral test to be really on the low, So I would agree with this, with this guideline that the integral test should be on the low end of the, of the priority for the test. Because, number one, you don't want really to, you really don't want to spend your time, using integrals to evaluate, the convergence or divergence, or determine the convergence and divergence of a series. Okay. Mainly because some of the expressions are not really that integrable. Okay. So I'd really put that integral test into the low end of the priority for which test to use. So that I would not really use them. I would just use them if the series, of the series would actually have a form that I think is integrable, such as this one. Okay. Um, Actually, this one lends itself to be, the form of this one actually lends itself to be evaluated or, tested using the integral test. Okay. From the form of it pa lang, parang, the integral test, uh, eggs you to use it for that particular series. Okay, but for others, no. I don't see the integral test, inviting me to use them in the other tests. Okay, so I hope that, you can practice the use of these guidelines into these sequences. I mean into this series, so that you can, get a grasp of how the thinking process is done in order for you to come up with which test to use in each of those cases. Okay. So now that we're done with, we're done with, the tests for your infinite series. We'll try to apply, this series into, into number one, into approximating other functions. Okay. In which case we will have to discuss what we call um the Taylor polynomial. Okay. And, number two, um, we express functions in terms of what we call power series. Okay. So how can we express these functions as power series? Okay, this is that part is now important because, um, that is the very core of what we would like to discuss on the next topic. Okay, which is the use of the power series method in order to solve differential equations having variable coefficients. Okay. So the next four topics would actually be dealing with the applications of this infinite series.